In this video, we're going to introduce Lagrange multipliers. So, suppose that we want to find the maximum and minimum values of some function, z equals f of x, y, and we're going to force our solutions to those maximum or minimums to satisfy the equation g of x, y equals k. So, the situation we would have here is, let's suppose the circle that I have drawn on the graph, this is the constraint equation. So whatever maximum or minimum value we have, we're going to force the solution to be on the circle. That's what this g of x, y equals k idea is. So even though we've got lots of different points that we could possibly plug into the function, the only ones we care about have to lie on, in this case, this circle. All right. So the idea here is, okay, so we're going to require the solution to be on this circle, or on this curve more generally. We're going to follow this until I make my f of x value, f of x, y value, be as big as possible or as small as possible, depending if I'm looking for a maximum or a minimum. So let's just say, for argument's sake, that these level curves up here in the upper right-hand corner, these correspond to larger and larger values of c that give us the level curve f of x, y equals c. So maybe this is f of x, y equals 1. This is f of x, y equals 2, 3, 4, 5. Just for argument's sake, say that those are the level curves. All right. So we're going to come along here and we're going to follow this circle. Notice that I wouldn't stop here or anywhere along here, because notice if I try to stop here, I can go a little bit farther and my function's going up. The values are getting bigger. So I didn't maximize it. And since their functions are going up, I certainly didn't minimize it necessarily, because I have to consider going the other way, perhaps. But I certainly didn't maximize it. And the more I move, the bigger the function values, until I get right here where they're just touching, and then the circle starts to curve away from the level curve, and now I'm starting to get smaller again. Okay. So at the point AB, where the level curve and the constraint equation are tangent to each other, that's where we are as big as we can possibly get, where those two things are touching each other, right? Because again, think about it. If I'm following this along and these level curves correspond to increasing values of c, then as I'm going across on this curve, my values for the function, I'm thinking about putting these points into the function, they're getting bigger and bigger and bigger until I just touch, and then I turn away, and now they're getting smaller and smaller again. So this would be where we would get the biggest possible value of the function subject to being on the curve. All right. Well, since these two things are tangent to each other, that means their gradient vectors have to be parallel to each other, or scalar multiples of each other. So as long as the gradient for the constraint equation is not equal to 0, there must be some constant lambda such that the gradient of f is equal to lambda times the gradient of g. And it's this value of lambda that we refer to as a Lagrange multiplier. Let's see if we can put this into practice with an example. So this example asks us to find the maximum and minimum values of f of xy equals xy squared, subject to the constraint x squared plus y squared equals 3. All right, so we're going to set up a system of equations to solve. We're going to use the fact that the gradients have to be scalar multiples of each other to get two of our equations. The partial with respect to x for f is y squared. The partial with respect to x for our g is 2x. So our y squared has to be a scalar multiple of 2x. Our partial with respect to y for f is 2xy. Our partial with respect to y for g is 2y. So we have 2xy has to equal that same scalar times 2y. Because remember, we're saying the gradient for f has to be a scalar multiple of the gradient for g. Now, right now we have two equations, but with three unknowns, so it'd be helpful to get a third equation to help us solve this system. That third equation, remember, is going to come from the fact that we have to satisfy the constraint equation. So our third equation in our system will just be the x squared plus y squared equals 3, because the xy that we find has to lie on the constraint. All right. Now, again, in these problems, we're going to be interested in what the x's and the y's are. We can solve for lambda typically, but we don't care what the value of lambda is. We're just going to use it as a tool to figure out what the x and the y are. All right, so the first thing we need to consider is what happens if the lambda actually is equal to 0. Well, if the lambda is equal to 0, that forces y equal to 0. And then if you use the third constraint equation, you get the point. The x's have to be plus or minus the square root of 3. So this gives us 2 points to consider. The points plus or minus square root of 3, comma 0. Let's suppose now that lambda is not equal to 0. Well, if the y is equal to 0 and lambda is not, then that forces x to be 0, because you have to have 0 equals 0 on this side. Or excuse me, on both sides, essentially, for this equation. So, but x equal to 0 and y equal to 0 at the same time does not satisfy the third equation. So if lambda is not equal to 0, y cannot be 0. What that means is that from the second equation here, we can divide both sides by y. This is the whole reason why we needed to make sure that y was not equal to 0. Divide both sides by y and divide both sides by 2, we get x is equal to lambda. If x is equal to lambda, then y squared is the same thing as 2x squared from the first equation. So now we have a relationship between x and y. We can plug that into the third equation. That gives us x squared plus 2x squared, or 3x squared, equals 3. And that means x has to be plus or minus 1. At either 1 or negative 1, the y can take on plus or minus root 2. And again, getting that from the third equation. All right, and notice again, I don't really care what the lambda is. You could go back and figure it out what it is. In fact, it has to be plus or minus 1, depending on the x value from that equation, but it doesn't matter what lambda is. We're interested in the points where this function has maximum and minimum values, x's and y's, nothing to do with lambda. So we have 6 points to consider. The first two come from our first argument with lambda equal to 0, negative root 3 comma 0, or root 3 comma 0, and the other ones come from these 4 points by pairing each of these x's with each of these y's. So you get plus or minus 1 and plus or minus root 2 in the various combinations. These are our list of points where we can get a maximum or a minimum value based on lying on the constraint. So we're going to take these and plug them into the function and see what values we get, and then we're going to pick out the biggest and the smallest and tell us what the maximum and minimum values are. Well, if I put root 3 or negative root 3 comma 0, the function is equal to 0, because the y is 0 in that case. If I put negative 1 and then plus or minus root 2, well, in either case, when I square plus or minus root 2, I get 2. And then we'll multiply by negative 1 and get a negative 2. And if I put in 1 and plus or minus root 2, I'll get a positive 2. So the maximum we can possibly get is 2, and the minimum we can possibly get is negative 2, and the 0 doesn't give us anything in this case. Let's look at another example that deals with functions of 3 variables. Say we want to find the maximum and minimum values of f of x, y, z equals x squared plus y squared plus z squared, subject to the constraint 4x plus y plus 2z equals 12. So just like what we did for the functions of 2 variables, for functions of 3 variables, we'll set up our system of equations by setting our gradients being scalar multiples of each other. That's where the first 3 equations come from. And then our fourth one's going to be the constraint equation. So again, here we're just setting the partial with respect to x for f equal to lambda times the partial with respect to g, partial of g with respect to x. And then likewise for y and likewise for z. Notice that if our lambda is equal to 0, then the x, y, and z would all have to be 0, and that doesn't satisfy our third equation. So should be pretty clear that lambda can't be 0. Let's go ahead and just solve for lambda then. In the first equation, we get lambda equals x over 2. The second one, we get lambda is equal to 2y. And in the third one, we get lambda is equal to z. So those all have to equal each other. So using this relationship, we get y as a quarter x and z as a half x. We can plug those into the fourth equation. If we plug that in and simplify, we'll get all the way down to x is equal to 16 over 7. Well, we know that y is a quarter of x. That was this relationship here. So since y is a quarter of x, we get y as 4/7. And we also see that z is a half of x, so we'll get that z is 8/7. So we'll only get 1 point here. So to figure out where our maximum and minimum values are, we first notice that I could certainly make x as big as I'd ever want and y as big as I ever want and adjust z with an appropriate negative value and make this equal to 12. If I plug that in over here, I'm squaring, so everything here is going to be really, 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 really big if I make x, y, and z big enough. So I can make this arbitrarily large. So there is no maximum value subject to this constraint. That means when I plug the point into the function, I should be getting something that's a minimum value. And we do that in this case and get a minimum value of 48/7.